Well, we have now completed our review of the different types of cable-stayed bridges. And for the remaining 3 lectures, 1 today and 2 in a fortnight, we have 3 separate special themes. The first one I will deal with now is on the protection of bridges against ship collision. And next time, the first one will be on, in short, bridge aesthetics, guidelines for the aesthetic design of bridges. And the last one, I will tell you about my 40 years of experience with cable-stayed and other major bridges all over the world. As a fitting closure, and I guarantee you we will not have an exam on the last lecture with that experience. By the way, there are examinations coming up, and thank God there are now for you to look at already 2. The first ones had none at all, but still I will do my own exam preparation one morning, 3 hours or 4 hours. Mr. Depe will give you the date, where I will give you in the shape of the examination a repetition of what we've done. And I assure you there will be nothing in the exam which we have not dealt with in the preparation. I think it's a little bit too much asked of you that you shall know by heart 1,000 pages of script. So we will concentrate on the main items which can be checked. And my experience, I've now taken 2 exams. I mean, for me also the first time on the other, I was always sitting on the other side of the table. But the result was that there were good results, and I was quite happy that people somehow understood. But I know the pressures. I mean, I've been studying myself, so I think that's why I do the preparation for the examination myself. You will get that, well, you can load it down from the internet to take with you and make some notes. And then I assure you, if you are fairly sober in that morning of the test, you should be able to do it. Okay, Mr. Depe will give you the dates. Now, on the protection of bridges against ship collision. We'll deal it in some general notes. Then the main item, what are the impact forces? We have to know. And then what can we do against by discussing protective structures and a little summary. Now, we are talking about a real hazard. It's a real danger. It's not some theory where in the ultimate limit state we assume if we use a factor of this then it will fall down. No, it happens. Bridges have fallen down and many people killed. Just this little list here comes to about 300 people killed. And I mean, that's a considerable number. I've been involved with some myself. One is the, where is it? The Sunshine Skyway, somewhere in the 1980. There it is. Okay. Sunshine Skyway Bridge. I've shown you our composite bridge we had designed. The reason was why we had to design it, the bridge came down, and there were drivers. It was in a rainstorm, and there were several cars who dropped down, plus a bus with many people. So that came to 35 lives. Of course, there are even worse ones. but that's one I was involved with. And so we are really talking about something which is not just theory. It happens. And it's Murphy's Law. What can go wrong goes wrong. I mean, we have all the probability curves and what have you. I tell you, if a pier can be reached by a ship, it will be reached. Because the main reason for these accidents still is that at the steering wheel, the guy is blind drunk. All the beautiful theory, what you have with probability and things, people are drunk at the wheel. And when they are drunk, it doesn't matter whether they pass off this or this or this. So Murphy's Law, you have to take into account. What is reachable will be reached. It has quite an economic impact, even when you design new bridges. Because the cost per pier, we will see that in detail, I just give it in general, to make it safe against the ship impact can be very, very high. Now, we know already when the piers become more expensive, it's more economic overall to have greater span lengths. Whether the piers are expensive because they are 200 meters high or whether they have to be made strong against ship impact doesn't matter. Money is the same. So, very early in a bridge design, we have to take into account what ship impact do we have, what sizes of ship, what does it cost, and then we have over water, we have a minimum span length, which is the navigational clearance the ships require for regular passage. However, what may be the difference in cost if we, so to say, voluntarily widen the span length, thus increasing the cost for the main span. The cost per square meter goes up with main span. I think that's obvious. But save may be more in not having to reinforce the foundations against ship impact. That's an offset. And recently, when we were designing the bridge alternate for the Fehmarn crossing across the Baltic Sea, the main bridge, this was a main item, and they had very high forces there, Pedersen you will see. And so the design was quite a bit driven by ship impact conditions right in the middle of the Baltic Sea, just as one example. So we have to take this very seriously. The main item, of course, we want to know what are the forces we have to design the pier against. When I came to this business in the early 80s because of the Zárate-Brasilargo bridges in Argentina, we'll see an example, I looked into the literature and found there's nothing. Virtually nothing. There was Minosky, who did, for if two ships run into one another, he calculated a force which is proportional to the volume of the deformed steel, which may be very nice for shipbuilders, but we poor engineers can't do much with that. There was nothing. And so, as a typical example, I take the collision of the Newport Bridge, Rhode Island. We see here the heavily deformed bow of the ship. And we see here the, slightly spelled damaged pier of the Newport Bridge. That's a major suspension bridge. Very sturdy piers. Okay, the bridge survived. The ship at least didn't go down. And now, for this typical situation, a steel pier which can have plastic deformations and a very rigid pier, we'd like to know the impact forces. There was nothing. It so happened that I came up on publications in my hometown, Gestacht, near Hamburg, where the atomic power ship Otto Hahn was designed. At that time, in the 60s, I think, they wanted to have commercial ships with atomic power stations. Didn't work out later, but anyway. And so for these atomic ships, one had to design some protection for this atomic power station. And so there were tests made by Mr. Voisin, whom I got to know very well, at the Howaldswerft, I think in Hamburg, with models. You see the man here, and those were heavy, expensive models, and they were let down an inclined plane with a given speed, and the impact forces were measured. Lots of publications, and something like that always came out. There's first a fluctuation, a very, very short period. Basically, I say that's the pre-buckling. Before the thing buckles and so on, it stiffens up, but it's very short. And then we have, for a longer period of time, we have the average force. And that's where we all decided, yes, that's only a dynamic effect. We have to design for the average force. How big is the average force? And then, with my simple mind, I looked into the results and sketched something and came up with the relation that the impact force is proportional to the ship size, deadweight tonnage. Measured in deadweight tonnage, simple, with some factor there. And that was it. And then I said, okay, we use this formula, and then of course we have a certain scatter, because it depends on the make of the bow of a ship, whether it's very stiff. Take a warship, a very stiff bow, or whether it's very soft, say an oil tanker. And so we said, from all these tests and what have you, and Mr. Voisin, who was a ship engineer, helped me there a lot, we said, okay, this plus minus 50%, depending on the type of ship. Beautiful. And that gave the first handle there is, first formula to give something. And then we worked together in the United States on AASHTO. I was on the AASHTO committees and so on. And my good friend Mike Knott became in charge. And then they said, well, this plus minus 50%, that's all too difficult. We use the 70% fractile, and then we have that all well covered. I don't believe it, but okay, it's easier to calculate, I agree. And so then the formula became 0.98 instead of 0.88 deadweight tonnage, which is basically the AASHTO formula. And there are other formulas taking into account the speed. The speed of the ship has a little influence. Not very much, because the bigger the impact force for a given ship, the longer is the plastic area of deformation. The work which has to be done, there is kinetic energy which has to be killed by inner work of plastifying the steel. So it's not that you have always the same 2 meters plastified, whatever the speed is, and high forces, weight times labor is the weight times the force. But it's normally you have a constant force depending on the crushing or plastic deformation resistance times the weight. That's the inner work which has to take up the kinetic energy, 1/2 mv square of the ship, plus 5% water you have to take into account which runs with the ship. But not going into details. So this was then done. What I had found, we put basically into AASHTO. We have here the force versus time. The Eurocode, the old Eurocode, I have to say, used the same, basically. And then Mr. Pedersen came up, I think 1983, who made some theoretical calculations, and he came up with double. So there's a big discussion today. Who's right? Aichto or Pedersen? And as usual, people are careful. Eurocode, the old Eurocode, switched from what we did for Aichto to Pedersen. So it's open to discussion, and you have to read the tender documents for a ship very carefully and looking out what impact forces do I have to assume for the given ship and so on. Do I have to use Pedersen or do I have to have Aichto? That's quite a difference in cost. So it's not nice, but that's what the situation is. I can't keep that as a secret. Now, what is the truth? Pontius Pilate said in the Bible, what is truth? In this case, we don't know, but we can try with finite element simulations. And there I came across something at the Tongji University at Shanghai, where I know the head of engineering very well, and he gave me that. And they made finite element collisions with a real ship's bow formed and all these things. And this is what, over the time, what Tongji University came up with, which I'm quite satisfied is good enough in the range of the formula we made for Aichto, and think Pedersen is too high. Of course, I'm biased, you know that. What Tongji did, they modeled this type of ship's bow with all the decks and everything, and they modeled the bridge pier, and that was the outcome. Looks not unreasonable to me. Now they evaluated that for other things. They said, for example, well, good enough if we have a real solid wall, what I showed you, Rhode Island Bridge. But normally, the piers are a little bit flexible. And what happens now if we have an additional parameter, flexible piers instead of rigid? Okay, here we see. A rigid wall would give these forces over the time, and a certain flexible piers at the pile cap would give, well, in the peak, half of that. So it's quite important, if you want to reduce the forces, to take into account flexibility of the foundation, especially, of course, if you are on high piles. If you have a solid pier on rock, not much giving. But if it's on long piles, it helps. Every little bit helps to keep the price down to win the competition. That's the name of the game we are talking here. Then the other thing which I briefly indicated in the beginning, the time period. We have here one local peak. Then we have a local mean peak, and then we have a mean over time, a general. We decided, basically, at that time, we use the mean over time. And you see already, and when you say, no good, we use the peak, then you are where Pedersen is against what we have. So it's open to interpretation. And if you compare then, take impact velocity into account for collision forces, and see the difference between the absolute peak, the local mean peak, and the global mean peak, there's already a factor 2 in. And then if you say, okay, old Eurocode and Aichto and compare all that, well, I would say, if taking into account that we don't know what type of ship is hitting there and all that, it gives us at least an idea what forces to apply, and it has to be specifically stated in the tender documents. Now, Once we have established, in a way, the impact forces, then of course there come in all the probabilities and things like that. I'm not going into that. That's in, for example, H2 and other codes. What can we do about it? How do we protect our bridge against the consequences of ship collision? First of all, highly recommended, place the bridge and the piers out of reach. If the ship can't reach the bridge, it cannot do any harm. Simple, isn't it? So, an example, the old Tjörn bridge in Sweden, an arch bridge, 278 meters, nice. However, a ship could reach the arch where the arch comes down. Well, that's the old Tjörn bridge, and in accordance with Murphy's law, what can happen happens. There was a ship running into the arch and taking the whole ship down. No. Okay, now we've learned that. So we place the new bridge out of reach. We use a cable stayed bridge with piers safely on land, and you see that the same ship cannot reach any part. This is the new Tjörn bridge, done by Krupp. Our alternate wasn't successful. Another of our bridges, second Panama Canal bridge, of course a bridge across the Panama Canal. There's the one and only overriding consideration: thou shalt not hinder the ships in the canal. Nothing else interests the people who run the canal, who pay for the bridge. Okay, so it's very high, very far away from, and even far away that the widening of the Panama Canal, which is currently under work, can be taken up easily. So high enough, wide enough, no ship in the Panama Canal can reach the bridge. Yangpu Bridge, Shanghai, it was world record 602 meters in 1994 when I was checking that for the World Bank. The 602 meters came up from the condition no ship must be able to reach the bridge. We want it not out of the navigational channel. Think of the drunken sailor. Out of the water. So that's where the 602 meters came from, and we see here the foundations being built with also a little seawall against. That was it. Stonecutter, not the one you know, but our design, which came up second. It still hurts. We would have liked to do that. It's a nice bridge. Looks we had there also was a condition. You can put it ashore, close to the shore, but not in. It is on piles. Okay, now what happens if a ship runs into the seawall? Well, you can do it with finite elements, and you find certain force being exerted through the soil, say seawall, onto the foundation. It's nothing really serious, but it had to be shown. It was in the tender documents, so it was investigated. Portsmouth, south of England, they wanted to build a viewing tower. And we were the engineers with the architect there and won the competition. And of course, there are all the big sail competitions. The idea was to have a ship's sail reflected in there with the platforms and all that. Well, it had to be more or less in the water, so it could be reached by ships, and especially there are some ferries running to and fro, and even if a ferry loses its steering wheel or engine power and is drifting under the wind. Ferries are high. We don't like that. And now what was done then was, okay, we make an independent protection in front here, which can deflect and make this sort of a buffer. So even for a building, that's why I brought it here, it may be necessary, if it can be reached by ship, we have to protect it. So out of reach, we put the foundation out of reach, but with an artificial structure. The next possibility are artificial islands. If we can't put it on land, then let's put the land around it, if possible. Here is an example, Houston Ship Channel crossing. You've seen that in detail. It was possible to place this artificial island around. It works very nicely. If you put riprap stones on top, it holds for a long time. The difficulty can be if the water is too deep. You have to use a lot with an inclination, a lot of material, plus you reduce the cross-section of flow in such way that naturally that's all proportional. If you reduce the cross-section, the water speed goes higher, and though you may create an additional hazard by increasing the speed, plus it's hard to keep the gravel, sandstone in place. So that's the shortcoming. But if it's rather shallow, the water, it's a reasonable solution. We see it here for Sunshine Skyway, or you see it here for the Cap Shui Mun Bridge in Hong Kong. That's an artificial island. We can also try to guide the ship away. If it's going in the direction of the pier, we can use a guide structure to guide it away. Not frontal blow, but guide it. One example is the Kronprinzen Bridge in Berlin. Behind there is the new main station. Calatrava design, very nice, very involved. However, it so happened that during the design, they forgot all about them ships which run underneath the bridge. So if Calatrava won his bridge and won the design, the bridge was built, and only then people said, what the hell, we have these big ships running there on the Spree. Remember the first arch bridge I showed you, and these arches can definitely be reached by a ship. So, well, we make some guide structures, yes, very nice. The result was we have nearly as much steel in the guide structures as in the bridge. If they would have considered from the beginning and defined this must not there must be no structure in this part, beautiful. But they forgot all about it. We're all excited about Calatrava's beauty, and so they had to pay for it later. But it's not yet come down, and so far that's a consolation. Another example, Neckar Bridge in Germany. There was a redesign, and people were aware that, I mean, there are not ocean-going ships on the Neckar River, believe me, but enough that if they run in, to take the pier away there. And so there were some guide structures installed, decreasing from, I think, 20 to 12 meters the navigational clearance, but okay. So that was an example. And in the final stage then, when all was said and done, we have the strong, nice piers, and they can take a hit from those Neckar boats which run there. All very scientific, don't laugh. Of course, now we come to independent protections. Basically, it is helpful that we have the load from the weight of the bridge on the piers against, we have a hit. I mean, this vertical compression always helps to take up a moment. I think that's perfectly clear. But sometimes it doesn't help, very bad foundation conditions. We can't make it wide enough, and so we can't make it strong enough. We have to make an independent protection. Zárate, Brazo Largo bridges, I've mentioned those near Argentina, across the Paraná. We've done several bridges there, I've mentioned that. After the bridge was long done, the authorities said, we've forgotten all about ship collision. So it was tendered, and that was for me the reason to start and work on this 1980-82 ship collision thing and try to find out something. And so what came out after I had determined impact forces and things which wasn't there, said, okay, we need something strong. The bridge is done, we cannot reinforce that. So we said, okay, we use on piles, bad foundations, we use a circular concrete pile with a deflecting top, which if the ship ramps here, takes it away, and we use some timber fenders for the smaller boats, and all very nicely considered. And the contractor for whom we designed the original bridge, ke-28, they put a price on, and everybody seemed to be happy, except that the state said, wow, that's much too expensive. And they used then floating protections. That's what is in there, which I call is an administrative protection, but I have not much trust in floating protections. To start with, if you don't have a very special sort of bulbous bow, if you have a raking bow or pontoon, those will just run over this floating protection. Plus, it's very difficult to inspect the moorings at the bottom of the river and all that. So I say I take no good, but they had something in the books and said, we've done something for impact protection, but it doesn't work. Now here, what I mentioned, here we have an example, Sunshine Skyway Bridge, Tampa, Florida, where originally there were two superstructures like this. And during a rainstorm, a ship, phosphate freighter, ran into this pier. The pier came down, the second bridge half came down, and there were several drivers on the bridge in their cars which came down, plus the bus, I told you. 35 lives lost, 1980. And then a new bridge was built. I showed you that unfortunately our design, steel composite, lost against Jean Muller's concrete alternate, and that's his concrete alternate. However, we were then involved, it was just after the Zárate Brazo Largo investigation. With Mike Knott, I worked to make then the H-toe. And of course, since this was a bridge which was caused by a ship collision and 35 lives, the protection against ship collision for the new bridge was taken very seriously. No administrative protection here. And we used what we call in the US belts and suspenders. So we did it in two ways. First of all, the towers received protective islands, and the side span piers received dolphin protection. And then, for good measure, for the main towers, in addition to the artificial island, there was also a major dolphin. Now, this hopefully will prevent another downfall. And we did the dolphin similarly as I had originally considered for the Sarate bridges. Here we have good gravel on the bottom of Tampa Bay, so we don't need piles, but otherwise it's sheet piles basically with a concrete top filled with lean mixed concrete, timber fenders around, and that was something like 85, and nothing happened, thank God, to the bridge since then. Rosario Victoria in Argentina, across the Paraná, 350 meters. We see here already independent protections. That's the same river in Argentina where the Sarate bridges were, where they had the floating protection, which I don't like. Now here we have this situation. That was at the end of the design required. We worked there for contractors, Hochtief and others. This is the bridge. Upstream, downstream, that's the design ship with a given speed and all that, and it was not possible anymore because we have here 60-meter deep piles to make the bridge itself strong enough. So we had independent protections, although they are missing the vertical load from the bridge itself, as I mentioned, but it couldn't be helped, and that's a pile cap, concrete pile cap, bigger upstream, lower downstream, because the speed of the ship against the current is smaller than coming down. And we used, we see it here, that's an enlargement. This thing, they were then installed, and they work by plastic hinges in the steel pipes. So again, kinetic energy of the ship, 1/2 mv square plus 5% of water, has to be taken up by internal work, which is basically, if we use rotational hinges, the rotational resistance times the angle. Which means, if I have an angle here, I need quite some way between, you see, this has to be considerable to enable that plastic hinges are formed in the steel pipes. Well, that was all taken into account, and then the steel pipes were filled with sand, which increases their buckling capacity. If you try to bend a hollow steel pipe, it will somehow buckle. And you do not get the full theoretical plastic capacity. However, if you fill it, say, with sand, it cannot buckle and you can develop. So there were all these tests made, and so we proved that the kinetic energy of the ship can be taken by internal plastic work. Ship collisions can take very well place with the side spans as well as the main spans. Think of the drunken sailor. So the keel bridge I showed you formerly, where the pier is rather on the side, has upstream a rather solid protection, which basically has to be on piles with a pile cap to take the force of a Rhine River ship. Second Orinoco Bridge, Venezuela, I showed you. Similar problems as in Paraná. Long piles, 10 meters tied up and down. So sort of independent protection. You see, it's not connected because we have these deep piles. Independent connection around the piers. The bridge is done, to the best of my knowledge. This is not installed. Hugo Chavez is a little bit short of money currently, so hopefully later it will be paid. For the time being, the bridge is vulnerable against ship impact. So finally, we can strengthen the piers. If everything else fails, or if that is the most advantageous, we don't take it out of the water, we don't have protective structures, we just make it strong. And one interesting example is the Galata Bridge in Istanbul. Everybody of you who has been in Istanbul has gone across the Galata Bridge. That's just in the center of the bridge. And from, I don't know, hundreds of years, there was a floating bridge because it's very bad soils conditions. And we were the first ones with Thyssen, mainly ThyssenKrupp, to design a fixed bridge there, the Galata Bridge. That's our design there. It is, I have not mentioned, it is a movable bridge. It's not very a bascule bridge. It's not very often opened, but it has to be opened, especially because warships are lying here, and the army, or the navy better said, insists you can get in and out. And so we have the problems of the very deep piles. Of course, we have the bascule bridge. We have heavy earthquake. And we have ship collision from these warships going in and out. And did you have a look? Ist es verschwunden? Ja. So. Okay. Danke. Now cut. So these are contrasting requirements. For earthquake, we want it flexible so that it, isn't stiff and it takes the forces of an earthquake. For ship collision, it has to be strong, it has to resist. And there was then a compromise found, and I remember Dr. Kovac, who did all the dynamics for me here, did the design, and we discussed it, and he had beautiful animations where he showed what happened during an earthquake for this design and how can it take ship impact. So it was a compromise between the contradiction, flexible against earthquake and strong, sturdy against ship collision. In addition, it was said, well, the bridge is low over water, and what happens if, say, a warship or major ferry warship runs into the beam, not hits the piers, but runs into the beam. And then the requirement was that you don't have, that these side flaps don't fall down. And so there was then assumed that this, here the ship hits, the lock in the middle where the two bascules meet gives up, slides out, and this remains. And it was shown that this is also at least stable, so the whole bridge didn't collapse, but only this part. That was in addition, that's an additional story how to protect the superstructure or the beam of a bridge against high standing up parts of a ship. The Helgeland Bridge, I showed you 30-meter deep waters, deep water on rock, precast boxes filled with concrete, strong enough that the ships which are expected in that fjord in Norway can run against. Similar, the Uddevalla Bridge in Sweden, we have here, so to say, high water. This is out of the water, but that's in. And if we look, here's low water. The one which we have just seen is this one, where the water is higher. And You see there is nothing particular, there's just the pile cap, and we calculated that this type of foundation on rock and so on can take the impact force from the ship to be expected there. Now, to sum it up, the problem of ships colliding with bridges is very real. History shows that regularly, definitely every year, I'm not saying every month, although worldwide maybe every month, ships collide with bridges, and often it costs lives. And if sometimes you're more sensitive, you will find sometimes it makes it into the news, especially when there are more than several dead. It regularly is a news feature from all over the world. So it's a real danger, not just for cost, but for lives. And we have to be careful to make sure it doesn't happen. Also, it can have an important impact on the design of the bridge, because if a pier in the deep water is very expensive, it may to protect against ship collision, it may be overall more economic to widen the span and gain from less costs in the piers against more costs in the beam. That is very real, and if you design bridges, not just the Neckar River, I mean, that's not really the good example, but say the Baltic Sea. Right across the Baltic Sea, where you have big sea-going ships, it can influence the design, and if you forget it, well, your design will probably not win, because in the end it's too expensive. So remember ship collision from the very beginning, if possible. Then the main and first issue is, how big are the forces which are exerted by a colliding ship onto, say, the bridge pier? And from tests with sizable ship models, a formula has derived. It's the force is proportional to the weight size of the ship, measured in deadweight tonnage, which is worldwide accepted. The factor in front of the square root is a little bit subject to discussion. As I've shown you, there's a factor of 2. But there are also finite element investigations, which I would say these days should be done for all specific cases, not go by this rule of thumb formula, which is rather rough. I mean, it's to give you an idea. But try to model the ship which you have to, which is running often enough. Try to model the pier, also its supports, to get some, and then find out what forces, say, reach the foundation, the pier cap, and for that you try to design. And remember, do not be misled by these beautiful probability functions. The further away from the main span, the less the risk. Murphy's Law and the drunken sailor, remember. So then what can we do to mitigate the results of a collision, or to avoid a collision? First of all, the best is put the piers on land unreachable for ships, if possible. then the next one is to try and make them out of reach by bringing the soil to the pier, so to say, by having artificial islands, which, if the water is not too deep, can work very well, especially if you can do it on the shore and say, okay, instead of 30-meter more bridge span, I make a 30-meter bulbous island there. Then you can try to deflect a ship from the piers, which is reasonable, I would say, for smaller ships on smaller rivers. I've shown you the example in Berlin and at the Neckar. And if those things don't help because the water is too deep and too wide, then you can either strengthen the pier itself so that it can take, in a proper combination, of course, the ship collision. And for that, for strengthening, you always have the aid that the dead load of the bridge coming down, for example, at a tower, helps to withstand the horizontal force from an impact. If, for example, the bridge is already done and the authorities suddenly see the light and say, we must do something against ship collision, then you may not be able to afterwards strengthen the bridge. It may have been possible during the design phase, but when the bridge is set and done, very difficult. Then you may have to design an independent structure. Now, the bridge pier itself, which you strengthen, cannot deflect very much. Oh, I'm too long. So we are done anyway. I'm sorry, I was wrong. Yes, I thought 11:05. It's 10:50. Okay, so you have to have an independent support which must have way to deflect by yielding. Okay, thank you very much.